everybody. Welcome to section 3.7, where we're going to talk about rates of change applications. Short way of saying that is here come the word problems. Basically, we'll talk about how we can use derivatives to solve problems in like natural sciences, economics, things like that. So I just want to touch on a couple different types of problems that you'll come across. And before we get started, mention a little notation that we'll see again in the future. Starting by looking back at what we used to call the slope. So we always labeled this lowercase m as a slope, but that was only for linear equations. When we talk about the slope, we talk about the rise over the run, or the change in the y values over the change in the x values, and we get this ratio. So to move away from strictly linear equations and talk about an average rate of change for who knows what type of function we're looking at, they use the Greek symbol delta y to mean the change in y. And they use the delta x to mean the change in x. So we shift away to that simple slope, and we start talking about the average rate of change, which is given by the same formula, essentially. But they say this is the average rate of change in y with respect to x. So very specifically, how is y changing regarding us changing x? It could be increasing, could be decreasing on average, though, because who knows what the function looks like if there's a function that looks like this, and between x1 and x2, you're staring at this value and this value, then we've got two different y values associated with x1 is y1, associated with x2 is y2. And it looks like on average, our function is increasing. Again, we only care about between these two intervals, so we're not even really concerned about this entire straight line that we've got here. But we know that on average, we started here and we've increased to there at a certain rate. But notice that that doesn't tell the whole story. It doesn't tell us that the function decreased, then increased, hit a maximum, then decreased again, hit a minimum, then increased again. It just tells us the broad picture of we used to be here, now we're here. And so again, average rate of change. Average meaning taken over some sort of interval. So the book starts to sprinkle in this notation a bit more here, and we'll see this notation a bit later as well. So that's what we're going for. We're going for average rate of change. Trying to figure out what some of these applications are doing over a given time period. So a couple different things that I want to focus on are the most typical problems that you'll see when you start calculus, one of them being some physics-based applications. And you've solved problems like this before, but now you get to do it with rates of change. You get to do it with derivatives. So you've solved similar types of problems like this. One situation that we cover when we talk about, when I talk about physics, I mean in the actual three-dimensional world, talking about the positioned function, which is generally given by s of t. The velocity function. Now, I can't write down a specific position function. It depends on the object. It depends on gravity. It depends on the, is it moving through water? Is it moving through air? Right? So I can't write down a very specific function. It depends on the problem. The velocity function is usually given by v of t, which is just the derivative of the position function. Right? So you can find the velocity if you know the position function. And the acceleration function, denoted a of t, well, I can differentiate the velocity function to get that, or I can take the second derivative of the position function. Because if I differentiate the position function, I just get velocity. If I differentiate again, that is 2 times the position function, then I get the derivative of the velocity function, which is the rate of change of the position function. So how fast is that change changing? Velocity just tells us how fast the position is changing. Acceleration tells us how fast the velocity is changing, which is the change in the change of the position. Yeah, it can get a little weird if you keep going back and referencing the original position function. So I'm just going to pull up a few problems from the textbook, and I've got them on screen here. I'm just going to turn on this little display here, and that'll pull up the problem that I want to cover from the text. So this is number 8 out of the textbook in the homework problems. It's a lot easier than me just rewriting the whole thing. It's already there. Might as well just take it. And it does say that if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is s, which is our position function, is 80t minus 16t squared. So I'm going to jot that down. That's very important. 80t minus 16t squared is our position function given. And it does tell us that it has an upward velocity of 80 feet per second. That's where this coefficient is coming from. And part A asks, what is the maximum height reached by the ball? So we want to find the maximum height reached by the ball. Well, let's go with that first. There's actually a couple ways to do this. Since this is a quadratic, you could go back and rely on that vertex formula, negative b over 2a. You could do it that way, but since this is calculus, I'm going to do it more based on calculus. Notice this has a negative leading coefficient on the quadratic. So it does have a maximum height, so it does open down. It is a parabola that opens down, so it's going to hit a maximum somewhere. So what I can do is to find that point where I'll hit that maximum. Notice that my average rate of change is going to be 0. Or I should say my instantaneous rate of change is going to be 0. So what we can do is we can look at the calculus and say, I need to find where the slope of the tangent line is 0. Right? If I can find that point, then I can figure out what this value t has to be. So we're going to use calculus to our advantage and say, hey, I know when I have 0 rate of change, I have it at this horizontal tangent line, not before, not after. So if I want to see where that max height is or what that max height is, then I'm going to go for that. So I'm going to differentiate s of t, which notice is the velocity, right? So it's going upwards with some velocity, it's stopping at the max height, and then coming downwards with some velocity. So I'm setting that velocity function equal to 0, essentially. So I'll differentiate this function, and I just rewrote it so it's in descending order. You don't have to do that by any means. But I get something that looks like this. Now, what do I want to do with that? I want my slope for that tangent to be 0, means I want my derivative to be 0. I don't want any sort of positive or negative slope for my derivative, so I can take that derivative, set it equal to 0, and figure out what point that happens at t and s of t. So what that means is I've got 80 equal, I'm just going to add the 32t on both sides to make it look like this, and we'll divide by 32. And this will tell me that t equals 5 halves if I reduce that, right? 10 over 4, yeah, 5 halves. And t is in seconds. You can write that. So that tells me when it'll happen, but it does not tell me what the actual maximum height is. The maximum height is given by S of t, in this case, S of 5 halves. So our goal is to go find out what S of 5 halves is. So I'm going to go back and I'm going to say S of 5 halves is going to be equal to, and again, I can go back to either one here, negative 16 times 5 halves squared plus 80 times 5 halves. So we know when it happens. Let's figure out what that actual max height is. Doing a little math here, this will be 25 over 4, but then we've got negative 16 divided by 4, so that'll be negative 4 times 25, plus, I can do 80 divided by 2 right away. It's 40 times 5. So this should give us negative 100. 40 times 5, that'll be 200. So we get 100. And this was in feet, not meters. Although I was going to say meters, but it says feet per second. So this gives us the maximum height. Remember, be careful that the first number that you're getting is when it happens, not what the actual maximum height is. So now we found the actual max height. Notice it had to happen where we had that horizontal tangent line. At the beginning of this part A, we saw that we didn't really need calculus if we looked at this in terms of the vertex. So remember that vertex formula is negative b over 2a, comma, f of negative b over 2a, or in this case, I guess instead of f, it would be s. And we could plug in those coefficients, but be careful, the way they gave it to you is 80 is b, negative 16 is a. So negative b over 2a. Obviously, you don't have to do it both ways. I'm just going to show you the different way of getting that 5 halves. So I want negative b, like I said, is 80. I'm going to write it out in descending order. Over 2 times 16, or sorry, negative 16 was a. You can see it more clearly when I write it in descending order. So I get negative, I can reduce that, or sorry, positive, because negative and a negative. Positive 40 over 16, 10, yeah, it still reduces to 5 halves. So there's a different way of getting that 5 halves. Notice you still have to plug this 5 halves in back to the position function, because it's only telling you the variable t when it happens, but it's not telling you what that actual result is. So the position function tells you where you are. And then part B asks, what is the velocity of the ball when it is 96 feet above the ground on its way up? So we want to know what the velocity is when it is 96 feet above the ground. Well, first we need to figure out when that happens. We do not know when the ball is going to be 96 feet above the ground. We don't know for which value of t that is. It's at 100 feet at 5 halves, or 2.5 seconds. It's at 100 feet. So somewhere before that and somewhere after that is where it's going to be at 96 feet. But we don't know those numbers, and we can't just guess. So what we have to do is figure out those numbers t, and there are going to be 2 of them, just based on it going up, passing through 96, and then coming back down, passing through 96. And the problem is clear about that too. It wants to know, on its way up and on its way down. I'm just going to leave that because that's our position function. So we need to figure out where this is going to happen, which means I need to take my position function and ask the question, when is this going to be at 96 feet? When is negative 16t squared plus 80t going to be equal to a height of 96? What values of t plugged into this quadratic will spit out the result 96? And it is a quadratic. I always like to simplify things as much as possible, just to try and see if I can factor it. Of course, you could always just default to the quadratic formula if you want. But we need to figure out at what time it happens, so we know the proper time to plug into the derivative, because we don't know that right now. So I'm going to write it again in descending order. Got everything on the right-hand side, the left-hand side 0. So I've got my quadratic and it's set equal to 0. These numbers are too big for me to start trying to factor. They're all even. Let's start chopping them down. There's 8t squared minus 40t plus 48. They're all still even. Let's start chopping them down. I love when problems do this, because it gets you to a point where you just want to factor the thing. You can already tell right now this thing's going to factor. It's got to. And it sure does. All right, we need t minus 3 and t minus 2. That's way better than fighting with those big numbers. Yuck. So I just keep divide both sides by 2, divide by 2. I guess realistically I could have divided by like 8 on both sides, or 16 on both sides right away. But we got there either way. T is 3, or T is 2. Now we've got two choices here. One of them says 2 seconds. Clearly, if we're throwing the ball upwards, it's got to hit that upwards first. And then at 3 seconds, it's got to hit the downward position. All right, so based on the shape of the function, we know that t equals 2 is on its way up and t equals 3 is on its way down. So our job is to go find those velocities. How much velocity does this ball have on its way up? So the velocity, which is the derivative of the position function, looks like this. So I just need to plug each one in. So when t is 2, I'll have v of 2, which is negative 32 times 2 plus 80, which is negative 64 plus 80, which will give me 16 feet per second. And again, it has to go up. So this is at 2 seconds, aka on its way up. And then if I want to find on the way down, v of 3 will be negative 32 times 3. So I'm just plugging 3 into my derivative to get the proper rate of change at t equals 3. So this will be negative 96 plus 80. This will be negative 16 feet per second. Makes sense. It's negative because it's falling down. So that's at 3 seconds, aka on its way down. So we've got the correct velocity with the correct time stamp, and that solves part B. So again, be careful. We don't just want to take the thing from part A, like 2.5 seconds, and plug it in, and then ask for the velocity. What would the velocity be at that 2.5 seconds? Well, the velocity would be 0, because it has gone as high as it can and stopped. And at that 2.5 seconds, it's just sitting there. But then just after that, it's going to start to fall down. So it loses velocity as it goes up till it has no velocity. Then it starts getting negative velocity as it falls back down. So our job was to find that time t first that we need to plug into the derivative, and then we can get our proper answers. Okay, let me take that away for a second. And while I'm here, get rid of this. So we see a lot of these types of applications, and of course if you take a physics course, you'll do a lot of these types of applications involving velocity and acceleration and all that good stuff. Another type of application that I want to touch on is, I guess, more of a biology application, if you will. specifically speaking, I'm going to pick on this population function. All right, so population, usually they use like n for the number of people. And it's another function of time, so they use t instead of x. And they may use r or k up there. I guess it kind of depends. Some people refer to this as the logistic function, or maybe just population growth. But what it does is it models the growth of a population at any given time t. And it's not as simple as exponential growth, because that has no carrying capacity, as they call it. All right, so this planet is only so big, it can only carry so many people. Or if you think about like viruses, or maybe like a bacteria in a like petri dish. The petri dish is only so big, only so many finite amount of bacteria can fit in there. So they call that the carrying capacity is A, right? I should say this carrying capacity is A. Whatever that value in the numerator is, it can never grow beyond that value. The initial population always happens when t is 0, and if t is 0, you just get a over 1 plus b, because e to the 0 is 1. So you just get that ratio, a over 1 plus b. Right, so it has some nice built-in information to it. Of course, r is the rate that the population grows. And then t is your time. Usually time is just dependent on the problem you're working on. Typically it could be in years. That's probably the most common one that I see. But some populations grow so fast you might want to do it in days. Like again, bacteria in a petri dish, you might want to do it in terms of days, or maybe even minutes. Who knows? So I want to take a look at a problem that has this similar style of setup, which is one here. Let me see if I can get it so it fits. Yeah, there we go. We'll zoom that back in one more time. So I'm looking at number 26. I'll make sure you guys can see the function as well. It says the number of yeast cells in a laboratory culture increases rapidly initially, but levels off eventually. The population is modeled by the function n. They recall it f of t equals a over 1 plus b e to the negative 0.7 t, where t is measured in hours. Okay, this one's in hours. That's not too bad. And at time 0, the population is 20 cells. So that's our initial population at time 0. And it's increasing at a rate of 12 cells per hour. That's a rate, so we're going to have to relate that to the derivative somehow. It says find the values of A and B according to this model. What happens to the yeast population in the long run? So first, let's go ahead and take this model. I'm just going to rewrite it up here, so we're going to see it while we work with it. And it is A over 1 plus B e to the negative 0.7 t. So you can see our rate there. Now, the two pieces of information that they give us is that at time 0, or t equals 0, they tell us that n of 0 is 20. That's our initial population. When time is 0, I already start with 20 people, or yeasts, sorry. And then n prime of 0, our rate of change at time equals 0, aka our initial rate, is 12 cells per hour. Let's mark those down. So these are cells. These are cells per hour. I don't need to underline that. We'll just leave it there as what it is. So this is the information given to us, and our job is to find those numbers A and B. Well, let's start by taking that function, n of t, and setting it equal to 20 when I plug in t equals 0. All right, so I just plugged 0 in for time t. Now, what that means is that I have a over 1 plus b times e to the 0, right? Because this coefficient is now 0, or sorry, this power is now 0. So I just get a over 1 plus b. Hey, wasn't that what I said before where I talked about the initial population? It's always modeled by a over 1 plus b. I'm going to rewrite that. This is 20 over here. And let's take a blue, something so that we can just, that's not the answer, but I'm just highlighting it so we can get back to it a little bit quicker if we need to. The other thing that they tell us is that the derivative with 0 plugged in is going to be equal to 12 cells per hour. Well, first thing, in order to set that derivative equal to 12, we need to figure out what the derivative is. We don't have the derivative. So we need to first find n prime of t, and we can then take n prime and set that equal to 12. So when looking at n prime, it's a quotient. So I'm going to have to do the derivative of the top. But don't worry, a is just a number. So when I differentiate it, I get 0 times the original bottom. I don't really care what that is because I'm multiplying by 0. Minus the original top is a times the derivative of the bottom. Now if I differentiate this, derivative of 1 is 0. Derivative of b, e to the negative 0.7t. Chain rule says I'm going to get b e to the negative 0.7t, but then I have to multiply by negative 0.7, the derivative of that exponent. So I'm going to write it as negative 0.7b e to the negative 0.7t. All right, so you can see I differentiate this exponential function, I get that exponential function back. B is just a coefficient, so it just lives with it. But then chain rule says I multiply by negative 0.7. I wrote it out front so it doesn't look like a minus 0.7. So I'm multiplying this piece by, there's my chain rule. Chain rule I'm just putting in front. Then quotient rule says I need to square the bottom. And I do need to square all of it. So there's the bottom square. So a nice thing about this is that the first piece disappeared. I can simplify this down. Negative a times negative all this stuff is going to be positive. And I'm going to write 0.7ab e to the negative 0.7t. Again, commutative property for multiplication. I'm just going to sneak the a and the b together. That still gets squared down there. Now, this I can set equal to 12 because it is the derivative with t plugged in to be 0. So let's go ahead and do that. Let's take 12 is equal to 0.7 a times b e to the negative 0.7 times 0 over 1 plus b e to the negative 0.7 times 0 quantity squared. That means 12 is equal to, since this is the derivative with 0 plugged in, 0.7 ab. This is e to the 0, so I'm just multiplying by 1. 1 plus b, this is e to the 0, so that's all it is, 1 plus b squared. Now we can play around with these algebraically. I kind of have like two systems of equation, or a system of two equations here. Well, I was going to do that in blue again. So again, this isn't the answer, we're just highlighting it. But one thing I can do is I can go back and look at this and say, hey, a must be 20 times 1 plus b if I multiply both sides by 1 plus b. That's a good piece of information to have, because then I can steal this a and plug it in here, and then I only have b to solve. So I'm doing like a substitution here. I'm saying if that's a, and a has to be 20 times the quantity 1 plus b, then this is going to be 0.7. Here's a, 20 times the quantity 1 plus b, times another b, divided by 1 plus b squared is equal to 12. So I took this a and I just plugged it in right here. Now, plugging that a in is really helpful because I'm multiplying 0.7 times 20 times this 1 plus b factor times b, and then I'm dividing by a 1 plus b factor and another 1 plus b factor. That actually allows me to cancel out one of those 1 plus b factors, top and bottom. Say goodbye to the square now. So this tells me that I have 14, 0.7 times 20 is 14, times b over 1 plus b is equal to 12, which tells me that I have 14b is equal to, if I multiply both sides by 1 plus b, 12 times 1 plus b, which tells me I have 14b is equal to 12 plus 12b. Subtract 12b on both sides. This tells me that I have 2b is equal to 12, which tells me that b is equal to 6. Okay, now this is part of our answer. We do actually want to find b, so that's our goal. Our goal is to say b is equal to 6. I'm going to put it up there. Now that we have b is equal to 6, we can go back and find a, because look what a was. It was just 20 times 1 plus b. So this tells us that a is equal to 20 times 1 plus 6, which tells us that, and I might be getting in the way, yeah, this is getting in the way, so I think I'll close that up. A is equal to 20 times 1 plus b, so a is 20 times 1 plus 6, because we just found it, which means a is 20 times 7, which gives us that a is 140. So we can write down 140. Right, and the reason I'm writing them up in that corner is because I'm going to erase this for some more space, but I don't want to forget those numbers. So now that we've got a and b, we can actually properly write out the function with those numbers in place. That's why I say I'm going to get rid of this. All right, so I said I was going to leave those numbers up there, and then I immediately erased them. But that's okay. I remember them. 140 and 6. So this is our function. I'll say where, because they really ask for just a and b, where a is 140 and b is 6. So we can more properly write out the function with the correct numbers in place in the numerator and denominator for a and b, respectively. So that does take care of part A of the problem. Or I should just say, the first question they ask. Find the values a and b. Now we'll bring this back. Oh, I'm sorry. I guess you couldn't see what it was saying on the bottom there. So it asks us to find those a's and b's, and we've got those a's and b's. But then it says, according to this model, what happens to the yeast population in the long run? In the long run just means, as time goes on, eventually what is going to be the trend here. So for that second question, what they're asking is, eventually what's going to happen to this population? Is it going to die out? Is it going to explode off to infinity? Well, we can look at that really quickly and say that it has a carrying capacity of 140 cells. It can't go beyond that. What they're asking us to do is to find a limit as t goes to infinity in the long run, right, as long as we want, of our function 140 over 1 plus 6 e to the negative 0.7t. So it wants us to take t out to infinity. Now we can find this limit very easily algebraically. It is the limit as t goes to infinity of 140 over 1 plus 6. This is a negative exponent, so I'm really dividing by e to the positive 0.7t. Now as t gets large, e is being raised to a very, very large number. This denominator gets huge, which means this whole fraction goes to 0. So I'm looking at a limit as t goes to infinity of 140 over 1 plus, essentially that just becomes a 0. So I just get 140 over 1, which is just 140. So basically they want you to just say, in the long run, what happens? Interpret it. Well, in the long run, the population of cells will reach a carrying capacity of 140. Okay, so it'll max out its population. That is, yep, that's all they ask for 26. So let me close that little window again. Not that I have to, but we're going to move on to something a little different. So now let's look at some applications for economics. And some of these applications are fairly basic. Again, we're just messing around with the derivative. We're not really doing anything too fancy. But one thing that you'll see a lot of as far as word problems go is you'll see the cost function c of x. And again, it depends on the product, so I can't write down a specific unique function for it, but they call it c of x. They can talk about the revenue function, r of x, and the profit function. And there is a way to actually find the profit function. It is all your revenue minus your cost. So we have these three types of functions. Now, along with them, you can also talk about marginal cost. That is the cost of producing the next unit, and that is given by the rate of change of the cost function. Is your cost increasing or is your cost decreasing? That tells you about your marginal cost. Does it cost me more to make another unit, or does it cost me less to make another unit? Then we have marginal revenue. Again, same thing. Basically, it's just saying r prime of x. What is your revenue if you make the next unit? How is the rate of change of your revenue? Is it going up? Is it going down? And you guessed it, marginal profit. Is profit increasing or decreasing? Of course, we always want it increasing, right? So that is p prime of x, which is r prime minus c prime. If you take applied calculus, aka business calculus, then you see this stuff all day, every day. Let's see if I can find that problem I wanted to do. There we go. Let's see if we can get this to fit nicely. Oh, yeah, perfect. It's So don't be scared about that really weird looking function there for the cost function. And we're not going to use every single one of these. This one focuses on cost and marginal cost. So problem 32, when you look at 32, it says the cost function for production of a commodity is a C of X, or sorry, I said 32. Is that the one I wanted to do? Oh, that's why. I think I picked one out of the newer edition. Well, that's fine. We'll do this one. Right? Has to happen. It says that the cost function for production of a commodity is C of X. I'm not going to read it all out. It's all there. And it says find and interpret C prime of 100. So we want to first find the derivative. And then using that derivative, plug in 100 and see what we get. So let me copy down our function C, which is 339 plus 25x minus 0.09x squared plus there's a lot of decimals here, 0004, or is it only, nope, it's 3 zeros for x cubed. So for part A, again, it asks find and interpret C prime of 100. So first we need C prime, which is our marginal cost. So I'm just going to differentiate term by term by term, right? That's going to be 0. That's going to be just 25. And I don't know why they put it in increasing order as far as the powers go. They just do. Double that 0.09, you get 0.18. The x will stay there, reduce that power, plus 0.0012x squared. If I do that 3 times 0.0004, I'll get 0.0012x squared. So just power rule, not too crazy. C prime of 100, that means I'm plugging in 100 wherever I see x. There's 100. There's 100, but be careful, that one's squared on the end. So this is going to be 25 minus, multiplying by 100 just moves that decimal, so that's not too bad. Multiplying by 100 moves the decimal, and then multiplying by 100 again moves the decimal, so that's not too bad. So I get 25 minus 18 plus 12. So that'll be 19. So this will give us our marginal cost. Right? So C prime of 100 equals 19. And we're talking, I think it was just dollars, right? Cost function for a commodity. Well, actually, it doesn't really explicitly say if it's cents or dollars or euros. So I'm just going to go ahead and say dollars per unit. And then part B asks, compare C prime of 100 with the cost of producing the 101st unit. So this means that for part B, I already have C prime of 100, and I want to compare it to the cost of producing the 101st unit. That is C of 101 minus C of 100, because I don't want to know the cost of producing all 101 units. Marginal cost only tells me how much the next one is going to be. C prime of 100, or sorry, C of 101 only tells me all 101 units, what their cost was all combined together. C of 100 tells me the cost of all first 100 units combined together. If I just want to find out how much it costs to go from 100 to 101, then I only want that difference of 100 units were made, 101 units are made. Okay, forget the 100 first units. How much did it cost just to make that one more unit? So for that one, we're going to plug in 101, and then we're going back to our original function. So 339 plus 25 times 100 minus 0.09 times 100 squared plus, or what was I doing? Oh, sorry, 101 plus 0.0004 times 101 cubed. I have to take all of this and then subtract all of, and we're going to have to go to the calculator for this. This is just going to be pretty messy here. 339 plus 25 times 100. Now I'm subtracting the cost of the 100. But I do want to write it out so you can see exactly what I'm doing. And then we'll jump to the calculator. Make sure you're subtracting all of that cost and not just the first 339. And then adding this, subtracting this, adding this. Make sure that negative is being applied to the entire C of 100 amount. So I grabbed my calculator. Again, I was thinking of doing a different problem, but that didn't work out for me. So now we're doing this. 339 times 25 times 101, or sorry, 339 plus 25 times 101 minus 0.09 times 101 quantity squared plus 0.0004 times 101. We're going to cube that. So this gives us, for C of 101, I've got 2,358.0304. And I'm just going to do second enter, and I'm going to go back and plug in 101, or sorry, plug in just 100, and we'll get that subtracted quickly. So this one gives me 2,339 when I plug in 100. So I'm going to take that difference, and I get 19.0304. So it actually works out so that I get really close to that 19. So this is the cost of producing. Let me get that screen out of the way again. I'm writing down there. There we go. This is the cost of producing 101 units. And you're thinking, well, okay, so the rate of, if I made 100, the rate of change is going to be $19 to, make the next unit. It's going to cost me $19. Why is this telling me it's going to cost me $19 and 3 cents, a little extra there? Well, the marginal cost is only approximating the cost of the next unit. Because again, when you look at a function, say, you have like a function like this, and you look at 100, you can see that the rate of change at 100 doesn't exactly hug the curve, right? It's a straight line. So it's approximating it, but it's not getting it exact. But it's getting very, very close, because we're talking about being very close, just 1 unit away. So the marginal cost is a very good approximation to tell you what the cost of producing the next unit will be. But until we actually make that unit and figure out how much that cost us, we can't say that that's exact, because we haven't made 101 units yet. I can't tell you what the next unit's going to cost because I haven't made that unit yet. What happens if I make the next unit and the machine breaks down and I have to pay to get it fixed? All that stuff has to come into play. So in reality, when I look at C prime of 100, it only approximates the cost of making the next unit. It does not get it exact. And you can generalize this a little further into C prime of n units, and where you make n only approximates the cost of making the next unit, right? It doesn't actually give you the exact cost, but it is a very, very good approximation. Let's see where we're at. 50 minutes, that's not too bad. So we can stop there. Just focus on some of the problems that have, the physics, position, velocity, acceleration. classic problems. We need to know how to work through those using derivatives. Economics type stuff, we'll probably see this a little more in the future. Right? Cost, revenue, profit. We'll see more with the revenue and the profit later as well, but it behaves the same. And then, of course, the population growth is a popular one, but that gets more into exponential stuff. And the next section actually strictly covers exponential growth, exponential decay. So in the next section, we'll see quite a bit more of that exponential growth and decay stuff. So again, that's pretty short and sweet for 3.7. It's just some applications. And then we'll see you for 3.8.